Annyeonghaseyo. Welcome back to Automatic Control Systems lecture. I am Professor Kalyana Velvolu with the School of Electronics Engineering. In the last class, we discussed on stability. So, from now, we are moving into a new domain, is what we talk about system performance. So, from now, we are going to analyze the system performance, and we are going to also learn tools such as root locus and controller design in the later weeks. So, this is week 7 part 3 system performance part 1. So, when we say performance, we always look at the quantifying error. So, if you have a system, we have an input, we have an output, and then we get the error. Input minus output, we get the error. The error tells you how good the system is. If you have any system, we always calculate the error. By quantifying the error, how much the error is, we will be able to explain how good the system is performing. If a large error, performance is bad. If the error is very small or error is 0, it is a good performance. So, to quantify a system performance, we are going to actually look at defining error constants. These error constants are for various orders of signals, for step, for ramp, for acceleration signals, we have different error constants. So, that is the main focus of this lecture. Now, steady state errors. So, if you are looking at steady state error, it can be found by applying the final value theorem, and it can be given by the steady state ESS is limit t tends to infinity E of t, that is in time domain, or equal to limit s tends to 0 s into E of s, provided that the system is stable. The important aspect is we can only identify the performance if and if only the system is stable. We do not do any analysis for unstable systems. Before you do any error performance, error quantification, first we need to check whether the system is stable. So, for stable systems, we are going to quantify and develop the error constant. So, the error is defined as the difference between the reference and the output. So, the error is clearly defined as E of t, that is equal to R of t minus y of t. So, you have the reference, we get the output, we actually calculate the difference, and based on the error dynamics, we are going to say how good the system is. The point is, when can we directly subtract output from the reference? This is only possible if you have a unity feedback system. If you have a k here, it becomes error is R of s minus k into y of s. So, the error constants and error performance are only good for unity feedback systems. Very important, unity feedback systems. Now, let us take a unity feedback systems, and then we get the closed loop transfer function, or we identify the y of s equal to g of s by 1 plus g of s R of s. So, we take the unity feedback system here, calculate the closed loop transfer function. Now, once you get the y, I can calculate the error as R of s minus y. So, you can rearrange the terms as R of s into 1 minus g of s by 1 plus g of s. So, by rearranging and simple analysis, we can get E of s is R of s by 1 plus g of s. This is called error dynamics. Hence, we have the error constant is limit s tends to 0 s into E of s. This is the error steady state. So, once we get the error transfer function, I am actually trying to identify or compute the steady state error. The steady state error is limit s tends to 0 s into R of s by 1 plus g of s. So, this is only defined for unity feedback systems. Okay, very important, only for unity feedback systems. Suppose you want to do error analysis for non-unity feedback systems. For non-unity feedback systems, your error term will be R of s minus h into y of s. So, you can't really analyze the difference between error and output for a non-unity feedback system. So, when you have a non-unity feedback system, we have to convert the non-unity feedback system into unity feedback system. So, if you are wondering how, it is very simple. You can actually take a new system. So, if you do not have a non-unity feedback system, you can take this system and equate this system to like g dash of s by 1 plus g dash of s is equal to g of s by 1 plus g of s h of s. Solve this problem, find g dash of s. G dash of s will be your your unity feedback control systems transfer functions. So, we know from the block diagrams we can actually change the blocks, we can remove the blocks and everything. So, modify the system, you can easily solve for g dash f, where g dash of s will be the unity feedback system. So, that means this one I can actually write in terms of g dash of s. So, the same transfer function will be equal to this function. Once you solve the term g dash of s, that will be inside here. So, you can always use a simple procedure to transform non-unity feedback systems to unity feedback systems. So, now we can actually proceed to identifying the error constants for unity feedback system. First, we are going to actually study for unit step input, next we study for unit ramp, next we study for parabolic. So, if you compare, one is position, unit ramp velocity, unit ramp is velocity input, and the third one is acceleration. You see, or first order, second order, third order. So, this is the order of the error constant. So, we only have 3 here: step, position, velocity and error constant. So, let us take for unit step input. What we analyzed for the steady state error is limit s tends to 0, s into r of s by 1 plus g of s. So, now take r of s equal to 1 by s. So, your error steady state will be limit s tends to 0, s into 1 by s by 1 plus g of s. So, if you analyze, s's get cancelled, and so you have the expression 1 by 1 plus limit s tends to 0 g of s. So, this limit s tends to 0 g of s is dependent on the transfer function system of the system. So, we have no idea what the position, it can be any value, it can be 0, it can be infinity or any value. So, we have no idea, so it depends on the system. So, we actually term this one as k position, that is limit s tends to 0 g of s. This is what we call position error constant. So, I can write this one, the error as steady state error as 1 by 1 plus k position. So, this is how simple we can actually define the error constant for unit step. Similarly, we can also evaluate for unit ramp. For case of unit ramp, r of s equal to 1 by s square. So, I get s into 1 by s square, s tends to 0 1 plus g of s. So, if you simplify, I get s tends to 0, s will go off. So, I get 1 by limit s tends to 0 s g of s. So, you get 1 by k velocity, that is for unit velocity or unit ramp input. So, k velocity is limit s tends to 0 s into g of s. So, we define this term as k velocity, and also we call this one velocity error constant. So, the actual error will be 1 by k velocity, here 1 by 1 plus k position, 1 by k velocity, that is for ramp. Similarly, we can also analyze for parabolic input. So, for parabolic, r of s will be 1 by s cube. Similarly, error steady state is limit s tends to 0, s into 1 by s cube by 1 plus g of s. So, if you analyze, we can get the limit, then we define this limit s tends to 0, s square into g of s is 1 by k acceleration. So, k acceleration is limit s tends to 0, s square g of s is called acceleration constant. There is another way to remember this error constant. So, you have the k position is limit s tends to 0. So, what we have here is limit s tends to 0, g of s. Position, so you do not need any derivative. K velocity is limit s tends to 0, s. What is s? S is differentiation. Differentiate position, you get velocity, s into g of s, right. One s in Laplace domain is differential. So, in the same way, what is k acceleration is limit s tends to 0, s square g of s. 1s is differentiation, s square is 2 differentiation is acceleration. Position, velocity, acceleration. So, you can easily, if you understand the definition, it is very easy to remember the error constant. So, the actual error is 1 by 1 plus k position, actual error for velocity is 1 by k velocity, actual error for acceleration is 1 by k acceleration. So, in this way we can easily formulate the error constant. Again remember, the error constants are only defined for unity feedback system. So, now let us go into a simple example here. So, we have a closed loop transfer function of a unity feedback control system. So, it is already a closed loop transfer function. So, take this closed loop transfer function and then we try to find the error constants. So, it is asked to find the steady state error to a unit ramp. So, we want to find the steady state error for a ramp input. So, now first we have to find what is g of s. So, since the closed loop transfer function is given, but to find the error constant you need g of s, because the definition is for g of s. So, first compare the closed loop transfer function with g of s by 1 plus g of s, and then you can actually equate the system, find what is g of s. So, you can just do a simple analysis and then get the expression for g of s. Once you get the g of x expression, we can actually proceed to calculate the error constant. So, the steady state error is given by 1 by k velocity is 1 by limit s tends to 0 s into g of s. So, limit s tends to 0, g of s is given. So, you substitute, find the s equal. So, you get a minus k by k. Now, what is this steady state error? The error for a ramp input for this system is a minus k by b. So, this will tell us how good the system is performing for a ramp input. You do not need to test, you do not need to give a actual signal, but we can just do a mathematical analysis and find what is the error with respect to a ramp input. We can also find the error with respect to a step, we can also find error with respect to acceleration. We can do all the analysis here for any system. So, by identifying the open loop transfer function g of s from the closed loop transfer function and just use the definition. There are only 3 definitions. So, students can easily remember these error constants and then it can be very important. So, the error constants which we are learning now are very important for controller design in PID. So, in a couple of weeks we will be actually discussing on PID controller design, and in PID controller design it is very important we are going to use the error constants because we talk about performance in controller design. Now, let us have a simple another exercise. So, I have a unity feedback system here g of s, e of s, y of s, and then where g of s is given by this expression. So, a student calculated the position error constant as k position as limit s tends to 0 g of s. So, if you substitute you get 10. He concluded that the steady state error with respect to a step input is 1 by 11. So, if you remember the unit step error calculation definition, it is 1 by 1 plus k position. So, 1 by 1 plus k position, so 1 by 1 plus 10 you get 1 by 11. So, now is the student's conclusion correct? It seems to be right, but how do we be sure? The important is the system stable? We have no idea. So, the system If the system has any poles on the right hand side, then the system is unstable. So, we take the system, and if we analyze using our stability criterion, we can find that it has roots in the right half plane. So, if the system is unstable, we can't define error constants. So, you can clearly say that the closed loop system is unstable and hence the steady state error is undefined. So, it is very important that you need to check the stability of the system to make sure that your error constants are indeed right. So, the error constants are not defined for unstable systems. Now, let us go into one important aspect, what we call types of control system. This is slightly different. We haven't gone through this kind of a concept. So, what is type? It's very simple. What we are looking here is type of a system is just dependent on how many poles you have at the origin. The number of poles at the origin will tell us the type of the system. If you look at the various transfer functions here, you have 2 poles at the origin. So, this is what we call type 2 system. Here you have 1 pole at the origin, we call this one type 1 system. So, for a unity feedback system, the type of a control system is with respect to RFS is defined by the order of the poles at the origin. If a system does not have any poles at the origin, then it is type 0. If you have 1 pole at the origin, type 1. If you have 2 poles at the origin, type 2, simple. Why we are studying this one specifically is the type of the system influences the steady state errors. If you have a pole at the origin, it has a huge effect on the error constants. So, if you are calculating the error constants, knowing the type of the system is very helpful for the analysis. So, it has a direct effect on the steady state error performance. So, we are going to actually study the error constants for various types of systems. So, as I told you, type is the number of poles at the origin. For example, I have s plus 1 by s square plus 2s plus 1. The system does not have any pole at the origin, but instead if I have s plus 1 into s square plus 3s plus 1, this transfer function has 1 pole at the origin. This is type 1. Suppose I have 2 poles, it will be type 2. This is type 0. Very simple. The number of poles at the origin will tell us what is the type of the system. So, if you look at the type of the system, based on the type of the system, we have different error constants. So, we are going to redo for every type of the system. So, we are going to analyze for type 0, type 1 and type 2 systems. So, look at the type 0 system. Type 0 system does not have any pole at the origin. So, when you write g of s, you can write g1 of s by s of 0 because, and then it is a type 0 system. So, g1 of 0 will be a constant. So, if we actually substitute g1 of 0, it will be a simple constant term. It cannot be equal to 0 because it does not have any pole at the origin. Now, if we try to identify the terms for k position, if we actually are trying to identify for the k position will be limit s tends to 0, g of s equal to limit s dash of 0, g1 of s equal to k. So, for s equal to 0, we will get a constant because it does not have any pole at the origin. In case of k velocity, limit s tends to 0, s into g of s. So, s into g of s does not have any pole at the origin. So, s into g of s will give you 0. In the same way, acceleration, limit s tends to 0, s square g of s will give you 0 because it does not have any pole at the origin. So, you can't cancel. That means, for a simple type 1 system, you can imagine it is like s plus 1 into s square plus 2s plus 2. Now, if you substitute s into g of s, s will give an addition. So, this is non-zero. If you substitute, you get 1 by 2. So, limit s tends to 0, s into g of s will be 0. In the same way, k acceleration will be limit s tends to 0, s square into g of s will also be 0. So, once we find the constants of k position, k velocity, k acceleration, I can find ESS equal to 1 by 1 plus k position, you get 1 by k. This is for type 0 system. For unit ramp, what I have is k velocity is 0. So, 1 by k velocity is infinity. So, unit parabolic function, I get 1 by acceleration again also equal to infinity. So, what we observe here, a type 0 system can only perform for step signal. If you provide either velocity or acceleration signal, your error is going to be infinity. That means type 0 systems are not really good. Type 0 systems can only give you a constant error for step input. Even for step input, you can't get 0 error because your unit step error is 1 by k. So, this is for type 0. It does not really give good performance for the signal, for any signal. So, if you give unit ramp, you get infinity error, no bad performance. Unit parabolic, infinity error, so really bad. Only for step, you get a constant value. Next, let us analyze for type 1 system. So, type 1 system has one pole at the origin. So, that means it has one pole at the origin. Example. So, I have one pole at the origin. So, I can write g of s as g dash s of by s1. So, separate this pole and this function, I can write g1 of s. Now, g1 of 0 will be some constant value. Now, we can find the k position, k velocity and k acceleration. So, if you look at the expressions, k position is limit s tends to 0, g of s. So, you get limit s tends to 0, g1 of s by s, that is equal to infinity. Because we do not have, we have a s here, so that can cancel. So, then we have this. So, when s tends to 0, this s will get infinity. Now, if you are looking at the velocity expression, limit s tends to 0, s into g of s. The s will get cancelled with the other s. So, you get limit s tends to 0, g1 of s will be k value. Now, you get a constant value for velocity. K acceleration is limit s tends to 0, s square. So, s square you only have one pole, so you get 0. So, for k position you get by s, so by 1 by 0 is infinity, k velocity you get k, k acceleration you get 0. Now, this is interesting. Now, if you analyze the unit step, I get 1 by 1 plus k position, it is 1 by infinity 0. Unit ramp 1 by k velocity, you get a constant. Unit parabolic, you will get 1 by k acceleration infinity. So, if you are looking at this analysis here, that means a type 1 system performs better than type 0 system. So, if you compare the type 0 system, I get unit step is equal to constant error, ramp infinity, parabolic infinity. But if we compare with the type 1, I get 0 error for unit step, that is really good, we get 0 error. But ramp, I get constant error, better. Last time we got infinity for type 0, here we get constant error for unit ramp. Then moving to parabolic, we still get infinity error. So, comparing this one, compared to type 0, type 1 performance is better. It can at least give unit step 0 and a constant for unit ramp. If you compare unit ramp in type 0 system, you get infinity error. Now, let us proceed with type 2 system. Type 2 system is simple, we have two poles at the origin. If you have two poles at the origin, the error constants will be slightly different. So, you can separate g of s, g1 of s by s square, separate this term, we get the g of s. So, g1 of 0 will be some constant. In the same way, we can calculate k position, k velocity and k acceleration. So, if you identify that, because of s square term, you get infinity, k velocity s0, g1 of s by s, you get infinity here for also k velocity, and k acceleration, you get limit s tends to 0 is k. So, only for k acceleration, you got k term here, but for position and velocity, you get 0 constant. Now, try to find the errors. The steady state errors for step, unit and parabolic, if you calculate, because of the infinity constants, we get 0 for unit step, 0 for unit ramp and constant for parabolic. That is very interesting because you are getting 0 steady state error for unit step and unit ramp input, but for parabolic I am getting a constant. So, if you compare all these three, type 0 is giving infinity error for ramp and parabolic, type 1 is giving infinity error for parabolic, but if you go to type 2, you get 0, 0 errors, very good performance, and get a constant error for parabolic. So, adding a 0 at the origin is improving the steady state error performance. So, type 2 system performance is better than type 1 and type 0. So, type 0 has the worst performance compared to type 1 and type 2 systems. So, let us go through this table here that gives us good idea about the steady state errors. The steady state errors for various input and system types are summarized below. So, if you look here, type 1, the first column is 0, 1, 2 type, and then we have 3 here, ramp, step and parabolic. So, if you compare all these 3, for type 0 I get constant error for unit step, infinity error for ramp, infinity error for parabolic. If you are looking at type 1, I get 0 for step is good, but constant error for ramp and infinity for parabolic. This is better than type 0, but if you are going to type 2, you get 0, 0 and then constant. And then higher types 3, 4 are not common. Okay. Coming to here, important point, most we only use type 0, 1 and 2, most common are 1 and 2, even we do not really like going for 3. Adding more poles at the origin may make the system unstable. So, it is not really good to have more more poles at the origin. So, in most of the analysis we limit the systems type to only 2. So, systems having a type higher than 2 are very uncommon and they are really difficult to stabilize, and their dynamic errors can be very large because they are very highly dynamic systems. So, that is the reason we only analyze type 0, type 1 and type 2. So, that is the reason why you only study type 0, type 1 and type 2 systems. In the next class, we will continue with the system performance and we will analyze the error constants for systems with disturbance inputs. So, this will be the end of the class. I would like to thank you. This is end of week 7, part 3. Kamsahamnida.